This speeded up film shot from above the Pacific gives you some idea of airflow over the surface of the Earth. Here's a hypothetical airflow on the Earth's surface. An enormous vortex in the northern hemisphere and another one in the southern hemisphere. At every point, there's a direction and a speed for the flow. We've represented the speed by the lengths of these arrows. But in the center of a vortex, the speed's zero and the direction's undefined. So if you dropped an object into the center of this vortex, then ignoring any updraft away from the surface, the object wouldn't be blown about sideways at all. Points like this, where the speed's zero, are called singularities or rest points. And there are lots of types of singularities, not just centers of vortices, as you'll see later. But now, just imagine that the Earth were a torus. Could we have the same kind of flow with the same pattern of singularities? Well, this pattern isn't the same. There's a single vortex here, and these flow lines indicate that there's a second type of singularity just above it. The flow goes outwards in these directions from this point, but it comes inwards along these. And at the point itself, the speed's zero. Well, it turns out that although you can have lots of different flows on either the sphere or the torus, the pattern of singularities can never be the same on the two surfaces. We'll prove that by the end of the program.
Let's look first at what's meant mathematically by a flow or a vector field. You've probably met the idea before on the plane R2. When we say we have a vector field V on R2, we mean that to each point xy, we assign a vector V of xy. These vectors then define a flow on R2, consisting of curves, such that at each point of a curve, the vector of the field is tangent to the curve. This flow is actually similar to the one you saw on the torus. Actually, there are some technicalities about the field V. It has to be what we call smooth. Well, mainly, that just means there are no sudden changes in the vector's size or direction. So, in any small region which doesn't contain a rest point, all the vectors have approximately the same size and direction, whereas vectors which are close to a rest point are close to zero size. Right, now let's look in more detail at what kinds of flow you can have on the torus and the sphere.
The rules of the game that our field should be smooth mean we can model a field by taking a hairy surface and actually brushing it smoothly. Think of these hairs as giving us directions when they're brushed along the surface. And for my first attempt at the vector field, I'll brush all the way round the equator. Then I'll carry on brushing round the circles of latitude. Here's one I finished earlier, similar to what you saw at the beginning. There are two vortices. Now, if I brush the same way on a hairy torus, I don't get any singularities. I can brush the whole thing smoothly, and I get a uniform flow. And here's one where I brushed along the meridians. And again, there are no singularities. If I try that with a sphere, brushing southwards along the meridians, then I will get singularities. At the North Pole, for example, I'll get a crown because I'm always brushing away from it. Then, of course, at the south pole, I'll get a tuft, which along the surface represents a zero vector. In fact, we call the crown a source and the tuft a sink. So for the sphere, we've seen two flows, both of which have two singularities. And as a matter of fact, no matter how you brush a sphere, you'll always get some singularities. Whereas for the torus, both these flows have no singularities. So is this the difference? Well, it's not quite as simple as that, because remember, we have seen a flow on the torus which does have singularities. So how can we make sense of all this?
Well, what's going on depends on the pattern of the flow around each singularity. What we'll do is attach a value to each pattern, which we call the index of the singularity. Here's a flow with a sink in it. To define the index of the sink, we first draw a simple loop around it, traced once positively. It doesn't matter which loop you take, as long as it doesn't enclose any other rest points. Then we look at each point P of the loop and the vector V of P, and we go round the loop, measuring how much the direction of the vectors varies during one circuit. The variation can be seen more easily if we base the vectors at a fixed point O. That is, for each point P, we take a copy of the vector V of P. So, the directions of the vectors vary anti-clockwise by one complete revolution. To put it another way, the curve traced by the sharp ends of the V0 vectors has winding number +1 about the fixed base point. And this is precisely the number we take as the index of the sink, +1. Let's try this out with another singularity. A source this time. Now you might expect that the index will be -1. Well, let's see. Again, we take a reference loop winding once positively about the source. And we do exactly as before. So in fact, a source also has index +1. Finally, let's try it with a vortex. So once again, we get +1.
In fact, the index of a vortex going in the opposite sense, clockwise, is also +1. It's not always going to be +1, by the way. We'll look at some different singularities later. But let's first see if the situation has become any clearer. For this flow, if we add the indices of the two vortices, we get the index sum of +2. And for a source and a sink, we also get index sum of +2. But for both these flows on the torus, there are no singularities. So we get index sum 0 in each case. Is this the answer then? Do we always get +2 for the sphere and 0 for the torus? Well, let's check the third flow on the torus, which does have singularities. We've got a vortex, index +1, and this complicated one called a cross point. What's the index of this? As before, we take a reference loop traced positively around the singularity, and we look at the vectors of our field at each point of the loop. and take copies of the vectors based at a fixed point. So we're going clockwise round our fixed point. So the winding number is -1. Actually, there are more complicated types of cross point with indices -2, -3, and so on. But this one has index -1. So the index sum is 0, +1 and -1. So all three flows we've seen on the torus have index sum 0. And the two flows we've seen on the sphere each have index sum +2.
Well, all this suggests that there's a genuine topological restriction on the kinds of flow you can have on different surfaces. That is, for a given surface, if you calculate the index sum for any flow, you'll always get the same answer. And what's more, as you may have guessed from the torus, 0, and the sphere, 2, that index sum is the Euler characteristic. We're going to devote the rest of the program to these topological results. First, we'll show why you get the same index sum from different flows, and later we'll show that it's the Euler characteristic. We'll restrict our attention to closed, orientable surfaces, because to define index sum, we need to know which orientation is positive, both for our reference loop and for the V0 loop around the fixed base point. So, given a closed orientable surface, we first want to compare the index sums of two different vector fields, say V and W. To prove V and W have the same index sum, we first choose a triangulation of the surface which avoids the singularities. And we also make sure that each triangle contains at most one singularity of V and at most one of W. Then what we do is take each triangle individually and look at the difference of indices in that triangle. So when we sum this over all the triangles, we'll get the difference of index sums. And we want to prove that this is 0. So let's consider an arbitrary individual triangle. And we'll start with the index of V.
We've shown some of the vectors of V based on the edges of the triangle because we're going to use the boundary of the triangle itself as our reference loop. So we'll travel around in the positive sense, A, B, C, looking at the variation in the directions of these vectors. The variation is anti-clockwise in this case, and during a whole circuit, the directions change by 1 revolution. So when we take copies of the vectors and base them at a fixed point, the variation loop will look something like this. And by definition, the index of V's singularity inside the triangle is the winding number VABC of this loop about the base point. The winding number happens to be +1 in this case. Now, before we deal with the index of W, we're actually going to deform W so that it coincides with V at every vertex. We look at each vertex and we take a neighborhood of it which is small enough to exclude all singularities. Then, within the neighborhood, we deform W smoothly until it agrees with V at the vertex. This deformation leaves the index of W unchanged because no new singularities have been introduced. So assume we've done that at every vertex. And from now on, we'll work with the new W, which has the same index sum as the old one, but which now agrees with V at every vertex. Because of these three agreements, we know that W's variation loop coincides with V's at the 3 corresponding points. That is, the point defined by W0A is the same as that defined by V naught A, and similarly for B and C. Now what about the rest of W's variation loop? Well, in fact, we want minus the index of W. So we go around the triangle negatively instead of positively. Then the variation in the W directions will be the reverse of the one we normally measure. In other words, the W0 vectors over here will swing round in the reverse sense to the one in our definition of index. So the winding number of the loop they trace will equal minus the index of W. The loop itself might look something like this. And remember, the winding number is minus the index of W. So the index of V minus the index of W is just the sum of our two winding numbers.
And now we're nearly there. We express each winding number as the sum of three terms. Now let me explain these six terms. VAB denotes the variation in the direction of V's vectors as we travel from A to B. So it's the variation about this point along this part of the V loop between V0A and V0B. And similarly, VBC is the variation along here and VCA along here. So all we've done is to split up this V loop into three components and then express its winding number as the sum of variations of the three components. And we've done the same for W, this time going in the negative sense along each side of the triangle. So for example, WBA is the change in W's directions as we go from B to A. So it's the variation of this part of the W loop between W0B and W0A. Now the reason we've put our sum in this form is that we can now express it as the sum of three new winding numbers. For example, RAB is the winding number of the loop bounding this shaded region. It's the variation along here, followed by the variation along here. In other words, it's the variation in the direction of V vectors going from A to B, followed by the variation in the direction of W vectors going from B to A. And similarly, RBC is the winding number of the loop formed by this part of the V loop, followed by this part of the W loop. And similarly for RCA. So we've replaced our two winding numbers by three winding numbers. And in this form, if we look at the sum over all triangles, we can easily prove it's zero. The point is this: in this sum, whenever RAB occurs, so will RBA. Well, that's because our surface is closed, so there'll always be a neighbouring triangle. And the surface is also orientable, so when we trace round this neighbouring triangle, positively, this edge is directed from B to A, opposite to its direction from our first triangle. Now, what is the loop for which RBA is the winding number? Well, we have to do the reverse of what we did for RAB. We have to go from B to A with the V vectors, and then from A to B with the W vectors. So the variation loop is just this top loop, but in reverse. And therefore, RBA is minus RAB. So when we add these two up, we'll get 0. And that's true for every edge of the triangulation. Each edge is represented in this sum once in one direction and once in the reverse direction from the neighbouring triangle. So the pair of terms for each edge always cancels out, which finally proves that the index sum of V minus the index sum of W is 0.
Well, that was a very long proof, so let me summarize the main points. We have two vector fields, V and W, on a surface, and we want to prove their index sums are equal. So first, we deform W without changing its index sum, so that it coincides with V at each vertex of a suitable triangulation. Then we determine the index of V in each triangle by tracing V positively around the triangle and taking the winding number of the variation loop. Similarly, we get minus the index of W by tracing W negatively around the triangle. Then the sum of the two winding numbers is the difference of the indices, and it can be expressed as the sum of three winding numbers. The winding numbers of this little outside loop, of this little loop here, and of this one. Finally, when we sum these terms over all the triangles to get the difference of index sums, we find we have to count each of these little loops once positively and once negatively from the neighboring triangle. Therefore, we get pairs of winding numbers, which all cancel out to give us 0. So V and W have equal index sums.
Finally, to end the program, let's show that the index sum is the Euler characteristic, faces minus edges plus vertices. We've just seen that when we calculate the index sum, we don't have to worry which flow we calculate it for. We always get the same answer. So we need only construct one flow on the surface for which this result is true. Well, given a general closed orientable surface, take any triangulation of it. Here's part of one. We're going to construct a flow on the surface which has exactly one singularity on each face, one on each edge, and one at each vertex. So we'll have a total of F interior singularities, E edge singularities, and V vertex singularities. Well, we're aiming at an index sum of F minus E plus V, so you can guess what index each type of singularity will need to have. Let's start constructing the flow. Concentrate on one triangle to start with. At each vertex, we'll put a sink. So each vertex has a singularity with index +1. Then on each edge, we put a cross point of index -1. Now for the singularity inside the face. It has to be a source, index +1. And we do exactly the same for each triangle. You can see that if we do this for all the triangles, we'll get a genuine flow over the whole surface. And that gives us our result. The contribution to the index sum from the interior singularities will be F. The contribution from the edge singularities will be -E, because each one has index -1. And we get +V from the vertex singularities.